Hey guys, thanks for joining me today. My name is Peter Rogers and I'll be discussing the improving of the 3D printing workflows using automation. A little bit of an introduction to myself. So my name is again Peter Rogers. I am based out of Tokyo. I look after the digital manufacturing group, additive manufacturing portfolio, including Netfabb, a little bit of power mill additive, simulation, and a little bit of fusion as well. I've recently been taking over the global additive cohort, and we've been working to improve the functionality and the way that we deliver the software. And so I look after the entirety of APAC, everything between India and New Zealand for additive products. So it's a pleasure to digitally meet you, and I look forward to spending the next 45 minutes or so with you, going over some of the things that we can do around automation. So just quickly going over the agenda for today, we want to have a quick look at some of the industry challenges, looking at some of the existing workflows, some of the known hurdles, what Netfabb is, as well as having a look at how we can unlock the potential of Netfabb in order to automate the processes. Of course, automation is a very, very ROI-focused functionality within any software, so we want to have a look thoroughly at some of the ROIs that we can look at achieving with some of our customers. So in terms of looking at the value of additive, I just wanted to start by giving a quick perspective of the way that additive is being used today and the way that we're looking at doing it in the future. So firstly, at the moment, the functionality that is applied to parts is relatively limited by the materials and the manufacturing method. However, with additive manufacturing, we're seeing a number of different new functions being added within the parts. So, for example, a part that was previously just being used for one specific purpose is now starting to take on multiple different functions, whether it be not just lightweighting, but also having a look at improving thermal dynamics, as well as looking at improving flow rates. A number of these different things are coming from the functionality of that part, and that is something that is starting to be designed as a function within that individual geometry. Some of the other things that we're looking at is additive for integration. So this could be anything from taking multiple parts, breaking them down into what their functionality is, and then building them into one part. For example, we have seen multiple times where anywhere between 20 to 100 parts are able to be collaborated into one individual geometry and 3D printed, which also helps to calculate and assist in knocking down some of those knock-on costs that are going to be gathering up as you start to look at the supply chain, as well as looking at some of the assembly costs that will be coming with the requirements of doing that assembly. And one of the other things that we are looking at doing is pre-production additive. So this is anything between visual aids, prototyping, anything to confirm the part and the geometry prior to taking it to mass production in a different manufacturing method. This is generally the one that we see most people starting off with in additive, as it is a very, very easy to develop cost analysis. Not having to make molds every time you want to do quick iterations of designs is very important. So this is an area that additive has been very successful in. And because of the new design tools, we are starting to see more of this additive for integration and additive for function. So with this, we understand that there are a lot of different positives and there are a lot of different ways that people are using additive to improve their products, but there are also some known industry challenges. Some of them are around design. Again, making sure that you have the right design going into the machine and making sure that you are getting the best value out of that part is something that quite a lot of engineers are still having issues trying to figure out the best way to design for. Another thing that we're looking at is the speed and cost. Relatively similar in terms of the outputs for both of these. Again, speed relates directly back to cost, so I like to bundle these together. But making sure that we are getting parts out of the manufacturing technology as quickly as possible in order for them to start manufacturing the next round of products that we want to be putting into the machine, but also looking at the cost-effective points in order to make sure that the machine is deriving the greatest ROI possible. So these are some of the things that we are looking at. And one of the things that is relatively slightly more unique to repeatability is that there is a lot more opportunity for production level parts that are built in one machine to be sent across to a different machine and have relatively different results in terms of geometry distortion, as well as looking at density of parts, And quite a lot of that can come down to the way that they are being prepared by the different engineers, as well as some of the aspects around material handling and these sort of things as well. So the repeatability is something that still comes up as a relatively large hurdle in order to take parts to distributed manufacturing or larger scale production. So I don't want to focus too much on design, but I do want to address it as it is still a relatively large area. So having a look at some of the capabilities that Autodesk have in this space is looking at topology optimization. Again, taking a standard geometry that you've been producing in other methods, removing as much material as possible in order to achieve lightweighting, and using that geometry and using 3D printing to manufacture it. So this is just one very basic way, and I think that most people are relatively comfortable with the idea of topology optimization, using simulation to figure out where is not required and removing that space. Lattice optimization is something that is a little bit more specific to additive, and one of the reasons for that is because we can create quite a lot more of these complex shapes within the parts. So again, very similar to what we do with topology optimization, we insert these lattices into the geometry, apply the load cases, it does an analysis, and it thickens up certain areas of this design. This is why you'll see that some of these areas are thin and some of these are thick. The reason for this is because there's going to be a lot more pressure, and in order to avoid the geometry not being suitable for actual end use, we make sure that it's going to be suitable for those FEA load cases. And the last one, generative design. It's a very large topic, so I'm not going to go into that. I'm sure there will be a few different sessions that we can watch during the summit. So make sure to check out the generative design functionality as well. So now that we've had a very, very quick and brief introduction to what some of the design capabilities are, I want to start to look more at the automation side of things and the way that we can improve the production of our customers. So what I want to do today is I want to be focusing on the actual end value, but in order to do that, what I'm going to do is I'm going to focus quite a bit on the HP 3D printing machines. And one of the reasons for that is because we are, of course, relatively large users of HP. We have 2 machines in our Toronto and Birmingham facilities, so we are very familiar with them. But the other thing is that they have a lot of benefit from automation. I will go into that in a moment. In terms of the expected workflows for these technologies, a lot of people would expect the term printing being in the name. They think about the way that they would generate a Word document, click print, it would go to the machine, and it would come out the other side. That is the expectations. When it comes to reality, it's not that easy. So quite often you will have people that generate the CAD. Once the CAD preparation is done, they will send it to a team that's going to prepare it for manufacturing. And quite a lot of the time that will be data conversion followed by STL checking and repairing, making sure that the mesh is going to be a solid mesh, ensuring that the minimum criteria for the machine is being met. Quite a lot of the time this will be minimum wall thickness. There will also be minimum feature size, minimum gap between parts, these sort of things. And once we have that confirmed, we also then do a trap powder or resin check. Because it is going to be building it up layer by layer, if we do not have efficient ways of getting powder out, then there could be the opportunity for powder to get trapped in. So we want to make sure that there is no areas that have a negative volume within that part. Next, we look at going at 2D or 3D packing. Once we have those 2D or 3D packing capabilities checked, we will go into a packing distance check to check how much distance is between each part. And based on that, we can understand whether or not we need to add more parts to the build or if we need to bring some out in order to relieve some of the energy being absorbed into the powder. So that's, again, looking at the layer density check as well as the packing density check. And then once we have that confirmed, once we have the build prepared, we go into the slicing and exporting to the machine. That's when we finally get to the step that people generally expect to be a little bit easier, and then go into the physical part preparation. So in general, there is a very large amount of work that needs to be done to confirm each part is suitable for 3D printing. And that average workflow would look at being about 5 to 8 minutes per part on average. Once you've done it for one part, again, you can create multiples of that part within the machine at the same time, which is relatively fine. But if you are going to be looking at a brand new geometry, this is roughly the amount of time that you would be looking at doing that check. So why does that matter? So again, we're looking at the HP multi-jet fusion technology here. One of the reasons why that is important is because the image on the bottom right is what a general HP build pack would look like. As you can see, there are multiple different types of parts within that build. You are going to have the ability to have many, many parts within that, as well as having high variety. So if we look at some of the strengths of HP Jet Fusion, the full build zone is what's available to be used. If you aren't packing it as densely and as smoothly as possible, then you can have the issue that you might not get as much out of each of those builds as you might be requiring. Some of the customers that we speak to, they're looking at getting between 300 to 500 unique parts into the machine at one time. Others that are doing more mass production, they might only have one design, but they're manufacturing multiples of that design at the one time. So there is a very good strength around this compared to looking at, for example, short life production of using injection molding. So there is still a very, very large amount of benefits to this technology. Some of the limitations of that, of course, as we mentioned before, each of these parts does need around 5 to 8 minutes of checking before it can be deemed suitable for 3D printing. And that can be a very large strain on engineering resources. So what we want to be doing here is we want to make this as smooth as possible. The other thing is that quite a lot of the time, the people that actually do the preparation for these machines are relatively highly skilled engineers, and they will be spending most of their time during their day checking these parts. So if we have a look at some of the things that can lead to is some of the known hurdles for mass production. So again, at the top, we're looking at mass production here, is that some companies will be, of course, looking for repeatability. If they've got a part that is in production that is being used in devices and they need to create a repair part or something similar, then what they will be looking for is making sure that there are no differences between the two parts that are going to be negatively impacting the usage of that end part that we are looking at manufacturing. So one of the things that comes up around this is looking at, for example, distributed manufacturing, where you might have a 3D printer in a factory in the US, in Europe, in Asia. If you send the design to that machine, you want to expect that that will be the same quality of part coming out of the machine, irrespective of where it is. So that is some of the things that we see around the repeatability side. The other thing is, of course, looking at cost. So when we are looking at having multiple machines, when we are having a high amount of parts that are going into the machines, we want to make sure that we can reduce the costs. And quite a lot of that will be around the amount of time that an engineer is required to prepare a pack. Again, one of the other things that does come up quite often is that they are very tedious manual data checks. So it isn't exactly the most engaging work. So in order to keep these highly skilled engineers engaged, sometimes we want to reduce some of this work. So that's one of the other reasons that comes up around costs. Then looking at scalability, again, we want to achieve scalability. And as I mentioned before, if we were looking at doing distributed manufacturing and having multiple additive manufacturing facilities, we want to make sure that we have a standardized process that is going to be able to be implemented very easily across each of these facilities. The reason why is because, again, if we have a different engineer preparing the build at each of the different sites using each of their different ways of doing it, there is a huge amount of opportunity for those parts to be very different between each of the machines and each of the different regions that they're produced. This results in potential for breakage. It results in non-standardization of part quality, which can reflect badly upon the brand. So we want to make sure that the builds are all relatively standardized. Now, if we have a look at the next slide, this again, at the top, we changed one word here, which is mass variety. So instead of looking at production level of a single or, up to 10, 15 parts, what we're looking at here is a company more like a service bureau that would be receiving a huge amount of parts, potentially one-off orders from 50 to 100 of their different customers. What that requires them to then look at is still there is cost and scalability are relatively similar, but the other thing is looking at speed. So they might have to do a lot of manual checks, and compared to mass production, there is going to be a lot more parts to be actually physically checking. So because of that, the data preparation time will skyrocket, and it means that there could be delays in getting the parts to the customer. The other thing, of course, is looking at the costs. If they are looking at a mass variety business, they will probably be a service bureau again, and service bureaus are, of course, looking at making sure that they are making money. So in order to make money, they need to cut the costs where possible. They need to make sure that they are getting the parts out as quickly as possible. And again, that means that they would either need to be quoting higher than they regularly would, or they would need to accept lower profitability if they were doing it in a manual method. The other thing, of course, is looking at scalability, but in a different way that we look at this is that if a very large B2B customer comes to them and says, we want to have this part manufactured at a very high rate, or we want to have a prototyping contract with your facility, then it could be an amount of designs that sends their capacity over the amount that they can actually handle, which means that they might have to reject certain jobs. The other thing is that they might require more engineers, and that would then also negatively affect their profitability because they have to take on more costs in order to deliver more parts. So what does Autodesk have to support some of these issues and some of these hurdles? So a little bit of a humble brag, again, 3D Software of the Year at the 3D Printing Industry Awards. Autodesk Netfabb is a very high-end software for 3D printing preparation. If we have a look at the general workflow that happens within Netfabb, we have the acceptance of design or CAD. We import it directly into Netfabb. We can do some basic optimization of latticing. We can do topology optimization. And we can also do surface latticing as well. We can then do basic repair functionality. As I mentioned, STLs have a lot of errors within them, so we need to check them sometimes. And if there are any errors, then we need to effectively repair them. We then need to look at either 2D or 3D packing. We then need to make sure that the part is going to be as close to the CAD as possible. So if required, we might need to do some near net shape adjustments. And then looking at the build supports if it is a machine that requires supports. Once we have done that, we create the toolpath, or we create the slice data that then goes to the machine. And in the case of metal 3D printing, there is a lot of stress that comes up with the powder receiving the heat and the energy from the laser. So that creates quite a lot of stresses within the part. And based on that, it will cause us to have to do simulation to make sure that there are no issues during the build. And once we have done that, then it can go to the machine. Again, this workflow, based on the conversations that we previously had about the HP workflow, a lot of this ticks most of the boxes of what people are doing with their HP technology at the moment. So we can take quite a lot of the work that they are doing, except for the base CAD design. Netfabb is not a CAD tool, but we have, of course, Fusion. We have a lot of our CAD tools that can do the base CAD design, and everything after that is what is looked after by Netfabb in terms of that additive manufacturing workflow. Because we have it all in that one tool, it means that we are able to take, for example, this entire workflow, and we can actually use what we call Lua scripting. It's a scripting language that is not Autodesk manufactured, but it is a relatively standard scripting language, which takes each of these different individual functions and workflows, and we can actually script them to make it so that it runs one after the other and delivers a end result, which could be anywhere along this process. So depending on the customer, what they want to be doing with Netfabb, but effectively almost all of the functionality within Netfabb can be operated using this scripting, which allows for automation of processes. So to give you a quick idea of what one of these workflows might look like, for example, a company might have 200, 300 different parts that have been uploaded to a Dropbox by a variety of different companies within their manufacturing group. And it could create a script that would be importing all of these parts. It would tessellate them, turn them into an STL. We could then, of course, do the wall thickness check. We could then, based on the passing or the failing of that wall thickness check, we could have all of the parts that have passed it going into a pass folder or a fail folder. Based on that, we can take all of the parts that have passed the wall thickness check, take them to a new, for example, in this case, an HP workspace, and we could 3D pack them based on the actual XYZ geometry of the build pack to make sure that we are getting as many parts in there as possible. From this workflow, instead of having 200 or 300 parts that they would need to individually check, what we can do is we can have it so that they only need to check the fail folder, and then that could make it, instead of looking and spending multiple hours checking and confirming that geometry is passed, instead they just have to look at the problem geometries, which could have specific areas that need to be fixed. So again, this is a great way for users to confirm geometries. And I just want to do a quick video of this to show the proof of concept of this that we have implemented internally, which is also being used by a number of our customers as well. So as I mentioned, we have the script here. It's fully customizable. You can edit anything in here. You can add specific functions in between certain things. And what this is going to do is it's going to bring in these parts. It's going to check the folder, which we have set up as files here. We have passing and failed folders for them to split the data into. We're going to tessellate and check for a wall thickness of 0.5 mil. So if we go into the pass folder and remove all of the parts that are currently in there, what this is going to do is it's going to allow us to have an empty field, and we have these files here, and one of these files is not meeting the requirements of that 0.5 mil wall thickness. At the moment, it's showing as 0.2 mil, so that is a part that we want the system to weed out. So again, based on the scripting, it runs it in the background. It imports all of the parts from the pass file, and we can see here that the part that was identified as not meeting the criteria is separated for an engineer to look at, and they might have to go in and speak with the designer that requested them to manufacture this part, because it's not going to be able to be created by the machine. Again, if we have a look at some of these steps that we went through here, of course, we did see that there was quite a lot of automation. You can, of course, pre-populate a lot of these windows that were popping up along the way. And based on that, then that is a very repeatable process. That is a process that is going to be applied to every single part in the exact same way. So there is less chance for human error or differences between engineers across different facilities. However, one of the things that people do pick up on is that we need to actually run this via the UI. So we need to open up Netfabb, we need to click Run Lua script, we need to select the script that we want to run, and it runs it based on human engagement. So in other words, it's a semi-automated process, but there is still room for improvement. So that's one of the reasons why we have started to implement our Netfabb application server. So what this is it's a resting server. It's effectively an API that connects to external services. So you might have an external storage system, or you might have an external distributed task management system that is triggered when you receive a new file. What that can do is it can use the API from Netfabb application server, or NAS, which will then send that information across to the Netfabb Lua script, and that will trigger the Lua script inside of Netfabb. So instead of having to do these manual engagements with the software, what this can actually do is it can work as a method for connecting your services to the Netfabb software. Where can you find specific information about this? GitHub. It's an open source framework so that it's very easy to use. People can build on top of it. They can implement it with their own systems. And if you search the link at the bottom, you can find all of this information here, or you can just simply search Netfabb application server on Google and it should pop up. So to give you an idea of what a workflow could look like using NAS and Lua scripting, is a designer has created a 3D design that they want to 3D print. What they can do is they send that to the server via a website, an app or something like that. And based on that, the manufacturer server would then use Netfabb application server, or NAS, to pull that information into Netfabb, and it would trigger a script. Once that script does, as we saw in the video, it processes all of that data. It would then take the results of that. It would push that workflow output to the server again. And depending on the design, it could send it back to the designer to say, this is sufficient for 3D printing. You need to improve the wall thickness in these areas. Or it could say, this is not a suitable design. There is problems with the STL, please confirm. Otherwise, it could literally just send it directly to the machine and begin the printing process. So there are a few different ways that we can use this, and it is fully customizable, so you can implement it in the way that you see fit. So based on that previous discussion around the design going through the server, having all of these different processes done, if it was a design that meets the criteria, you could have all of these things complete, and then you just send that geometry to the 3D printer for manufacturing. One of the other things that could be done, of course, is if that part was not meeting criteria, after all of these automation steps are done, we can actually send all of this information to Microsoft Office 360, which would then pull this information, and you can automatically import the information into a template that you have created, which could then automatically be sent back to the designer. So this is a great way of avoiding having to do all of these manual checks for the dozens or hundreds of designs that are coming through the customer's website or from their sales teams. And it allows them to scale up without the additional costs. So a customer that has implemented this effectively is a company called Solaris, based out of Japan. What they are doing is they are receiving designs such as this onto their website. Customers letting them know where the errors are in the design. What we have done is it's highlighting the different areas of the design in red that are not meeting the criteria. As we can see here, it needs to be a 0.8 mil wall thickness, and the areas that are 0.5 are not meeting that criteria, so they are highlighted. Similarly, these minimum features are not meeting the criteria, so they could have areas of failure. So we want to make sure that the designer is aware of these potential risks, and if they are and they accept that, then we can go to manufacturing. It's a great way of making sure that the service bureau is not taking on risk for potential failures within that print. So if we have a look at the cost-benefit analysis of going between manual and automation, so again, the manual process, there is a number of risks around and costs around the number of staff and the amount of skills to ensure that the parts are being manufactured as desired. By not having that standardized process, or even if it is standardized, having all of that standardized process built up in an individual or two can create large silos in capabilities. So what we want to be doing is standardizing that process and making it applicable for a variety of different places for them to do manufacturing. The other thing is, again, time and cost consuming. And if we have a look at this rough graph of what it looks like, we would have the total costs and the number of parts. Manual being in blue, you would see that it goes up relatively steeply as more time is more resources consumed. And then once you do hit capacity of the amount of parts that an individual engineer can take on, you might need to have a new hire in order to cover the amount of volume. So if there was the requirement to go an extra 3 or 4 parts here above what the current capacity of the individual engineer is, it would mean that they would potentially reject that work because it's not going to cover the value of that gap here. So again, there are a number of issues with manual processing. When we have a look at the automation side of things, however, we can see that there is the ability for it to scale at a relatively flat gradient in order to make sure that the automation is going to be delivering the parts in a cost-effective way. Again, they can take on more work without having to worry about a huge amount of increased costs. And it does allow them to achieve a very good quality of standardization across all of their builds. And this, of course, can also have knock-on effects to allow them to create enough paperwork and make sure that they have that standardization required for certification. And this can then further help them gain access to various other industries as well. To get a little bit further into some of the ROI calculations, I'm not going to go into all of it. You can read some of this in your own time, but the value that we're looking at offering is looking at a very simple cost analysis. Again, it's not taking into account every single part of the equation, but just a basic part time multiplied by the part number divided by 60 minutes per hour. So in order to find out how many hours we're going to be having to work on these parts. And then having a look at W, which is wages, and then multiplying that out per year. And then if we just look at a basic implementation and software cost setup of around $20,000 per year, we can have a very nice ROI calculation here. So if we were going to take a rough estimation of some of these, we can have a look at, for example, Service Bureau ABC. They will have 100 parts coming in. It takes their team on average 6 minutes to prepare each part, and their engineers are getting paid around $30 per hour. Based on this ROI calculation, you would be having a look at, again, 6 minutes per 100 parts. So that's around 600 minutes to do preparation. So that's about 10 hours worth of work, and we would have $30 per hour there, multiplied by the amount of days per week. Again, we're assuming that it's around 250 per year, and then dividing that by the cost in order to get the ROI. Based on this very, very, very rough calculation, we can see that there would be a cost savings of around $55,000 or an ROI of around 375%. And again, if we want to change some of the variables, for example, ABC Service Bureau has 6 minutes of preparation time and $30 as their average wage. This is the amount of parts per day that they would see coming through. And if it went above 40 or so, they would see that the ROI would actually be quite positive. If we have a look at the time variable, if they have 100 parts coming through per day and their wage is $30, then if their engineers aren't able to process the parts at 5 minutes per part, then the ROI is going to be very strong for them moving forward. And again, this is based on these various different constraints. And as soon as we see multiple constraints moving, this ROI calculation would move quite quickly. But of course, it's not just about the direct ROI. There are a number of other benefits that do come with having a automated process in place. And some of them are all listed here. So again, looking at knock-on benefits of that are not directly ROI is quite important. So we want to have a look at some of them. Standardization of process is going to be very beneficial for repeatability and certification. Freeing up engineering resources is, of course, something that's of high value to the customers so that they can start focusing on some of the higher value activities or building out new capabilities. Also looking at reduced costs is, of course, going to be something that's quite beneficial. That cost saving could be passed on to the customer, which could further increase the demand for the parts that are going through their machines. Of course, looking at 24-hour processing, this is, of course, something that is very beneficial. The amount of time that it takes you to get a quote out, or if there are any geometry issues, dealing with them quickly helps you to better close the conversion. So higher conversions means better business, and that can lead to a better revenue source for you there. Also then looking at reduction of human error. This is again something that is quite important. It connects back to standardization, also connects back to repeatability. And then having a look at some of these other points around scaling a business. So if you have one machine, going up to 2 or 3 machines could be quite costly in terms of engineering costs. Having, of course, faster and easier onboarding of new staff. If they can just do a 1 or 2 button click in order to achieve most of the work that they need to be doing, it really helps to ensure that they are getting onboarded faster. And that also can reduce the reliance on individuals within the company. Kind of connecting to the previous point, if it is all reliant on an individual siloed person, if that person leaves the company, we have seen situations where Service Bureau's quality instantly drops because they aren't able to produce the same quality as that engineer was able to produce. The other thing, of course, is less time spent on labor-intensive, tedious tasks. And if you have ever done these kind of processes before, you would know how draining it is. And by reducing the amount of time spent on these things, it can help to increase retention of staff. Improved data delivery is also going to then knock on to reduced machine downtime. And again, these are just a couple of brief points around indirect ROI, but there are multiple more. So at the moment, we've done quite a lot of conversation around plastics, but automation, as I mentioned, has functionality across the entire Netfabb portfolio. And there is a lot of automation that we can do for metal as well. One of those things that we have within that portfolio is looking at taking apart automatically orientating, automatically creating these supports, and then sending it for simulation to check how much distortion will happen during that build. If we have a look at these 4 different orientations, a skilled engineer would probably be able to tell you, okay, this is probably the best orientation for this build, but it would be more of a gut feeling than based on science. So what we're looking at doing here is creating a script that would be taking the capabilities that we have in-house, such as this specific 3D printer, this material, and what we would do is we would create the thermal and mechanical simulation files that we need to do a full part simulation of this. And based on the script, in this case, what we're going to do is repair the part, orientate the part for multiple different orientations, and use a standardized support script. Based on that, it's going to pull that information into simulation files, and it is going to run those simulations on these various parts. So as we can see, it has started to do the simulation based on this orientation and these supports. And these parts and these supports are already pulled into the thermal and mechanical simulation input files, so that when we open up simulation, it already has all of this information in here for us, and we can do a thorough check of what is going to happen during that build. What we can do now is we can have a look and say, okay, orientation 1 is really good because we can fit 8 parts onto that build platform because the surface area of the part on the base plate is quite low. However, it is going to have slightly more distortion than some 7 parts fit on the build platform in these orientations. But in terms of getting the best results, we might want to look at having this one in order to meet manufacturing lead time requirements, and we can just do a compensated geometry to make sure that we cover this displacement during the build. So again, the automation is able to take all of the variety of functionality within Netfabb. It can place them in a very ordered stack. It can run each of those different processes one after the other. And then based on that, you can have a specific output such as this kind of format here. And that will allow you to reduce quite a lot of the concern around which orientation is going to be best. But it also means that your engineers aren't going to be spending too much time creating this information for you. So it's a very good method of creating the orientation optimization. And that is it in terms of orientation for automation. So again, we had the conversations around HP's automation for plastic parts. There is the simulation capabilities and automation for metal parts. And there are a number of other functionalities that we didn't introduce here. So in terms of what you guys can do with the software, the sky's the limit. If there is certain things that you would like to optimize or automate within your current processes, let us know so that we can start working on it with you. Very much appreciate your time today, and I hope you enjoy the rest of the summit. Thank you.